Look at these two distributed traces. On the left, a standard Go service handler executes entirely in 12 milliseconds inside a staging environment. On the right, that exact same process requires 310 milliseconds in production. To understand why, we have to isolate the variables. The application code deployed to both environments is identical. The SQL queries being executed are identical. The underlying database hardware is exactly identical. The difference lies strictly in physical network routing. On staging, your service and database sit on the same machine, communicating over a localized Docker network with a round-trip time of 1/10 of a millisecond. In production, they are separated across distinct availability zones. Total latency in these systems is dominated by the physical transit time between network hops, rather than the internal execution speed of the functions themselves. Zooming in on a single query block from that production trace isolates the actual problem. The database only requires half a millisecond to process the query, but it takes 15 milliseconds just to transmit the data across the network. We can calculate the total handler execution time precisely. Total latency is simply the number of sequential calls multiplied by the sum of transit time and processing time. 20 calls at 15.5 milliseconds each equals our 310 millisecond total. The actual database work amounts to exactly 10 milliseconds. That means the handler spends 97% of its lifecycle in a suspended state, purely waiting for packets to travel between server racks. This structural flaw is known as latency amplification. When network calls operate sequentially, they act as a linear multiplier. Overhead scales directly with the call count, entirely independent of the actual data payload. Shaving a fraction of a millisecond off an individual SQL query yields zero noticeable improvement when your architectural structure inherently multiplies cross-AZ transit time by a factor of n. This IDE block shows a standard modular Go handler making 5 single responsibility data fetches in strict sequence, but expanding the lines reveals severe latency blind spots between each execution. This specific bottleneck effortlessly passes code review. Developers correctly assume that well-scoped, decoupled functions are best practice, but falsely assume that executing them sequentially automatically yields a performant system. The error lies in mistaking an assumed sequence for a true dependency. If the getOrders function does not explicitly require the output of the getUserProfile function to operate, stacking them sequentially is a purely arbitrary restriction. We resolve this structural defect by moving away from sequential steps. Using Go's errgroup package, we launch all 5 independent requests concurrently. Watch how this optimization alters the handler's execution timeline. Instead of adding the durations together, the total wait time simply becomes the duration of the single longest request. Parallelization changes the mathematical model. It drops the total network tax from an O of n multiplier straight down to O of ln. Resolving multi-region delay requires abandoning sequential execution for independent operations. By stacking these calls concurrently, you ensure your application only pays the transit penalty once. Applying parallelization to 20 queries against a single database introduces a new failure vector. Concurrent access exhausts the connection pool, creating a volatile backlog. The structural solution for sequential queries to a single data store is native pipelining. In Go, you accomplish this by utilizing the pgx.Batch API. The Batch API alters how the client behaves under the hood. It queues multiple independent SQL statements locally in memory, holding them back rather than initiating 20 individual external transmissions. Physically, this consolidates 20 individual packet round trips into a single unified network exchange. The client makes one request, and the database returns all 20 results. This method does carry architectural constraints. To successfully queue operations in a single block, the grouped queries must share the exact same transaction isolation levels and target the identical database connection. By refactoring the transport mechanism to eliminate n individual handshakes, developers strip away the cross-AZ tax, executing database operations at speeds nearly identical to local staging environments. Performance constraints tighten further if the primary database sits in a different geographic region, where baseline round-trip time climbs from 15 to 80 milliseconds. To mitigate this, engineers deploy local read replicas directly inside the exact same availability zone as the service itself, intentionally splitting the latency budget. This network map shows how traffic is divided. Local read requests hit the replica and clear in half a millisecond. The mandatory 80-millisecond cross-region tax is reserved strictly for state-altering write operations. This topology enforces a technical trade-off known as eventual consistency. Application code must explicitly handle replication lag, particularly when a user queries their own data immediately following a primary write. For data that requires repeated, continuous access, developers deploy an application layer cache. Fetching data in process completely bypasses the external network interface, avoiding external transmission entirely. You cannot write software that executes faster than packets physically traverse fiber optic cable. Manipulating physical data proximity is the only architectural method to overcome the hard limits of cross-region routing. These architectural failures persist in production because they are invisible during the development workflow. Zero-latency staging environments constantly mask O of N scaling problems from the engineers writing the code. We can permanently disrupt this staging mirage using netem, a native Linux kernel module designed for precise network emulation. Running this command forces the local staging interface to mimic a production environment, injecting a harsh 15-millisecond baseline delay into every outgoing transmission. Testing against a perfectly constant delay is insufficient, so we introduce 5 milliseconds of variable jitter. Real networks fluctuate, guaranteeing developers randomly trigger and expose timeout-sensitive code paths prior to deployment. By deliberately breaking environment parity and simulating multi-region latency locally, engineers experience the true cost of their logic loops. They naturally adopt highly concurrent O of 1 patterns during active development, rather than applying them later during incident response. This matrix outlines the strict hierarchy of structural fixes. For independent cross-service calls, parallelizing execution via errgroup yields the single highest impact reduction in total wait time. When an application makes multiple sequential requests to the exact same database, client-side batching is mandatory to shrink n round trips down to exactly one network event. For read-heavy applications operating in cross-region topologies, placing local read replicas and caches immediately beside your service is the only way to achieve zero-hop data retrieval. Extreme code-level micro-optimization is an ineffective misallocation of resources if the empty spaces between your functions are heavily bloated by unmanaged round trips. You must architect every distributed system under the assumption that every network jump carries a rigid 15-millisecond penalty, because in a multi-region reality, paying that physical tax is mandatory.